chapter of alcohols. If you remember where we left off, we were looking at the preparative methods for alcohols. And the two sort of mechanisms that we started out at the top of the page was the SN2 and the SN1. And we were sort of kind of recapping reactions from OChem1, weren't we, right? That first reaction there was the acid catalyzed addition of H2O, OChem1 early on. The next one was oxymercuration, demercuration, again, another OChem1. And I remember that whenever I teach this particular reaction we just finished up with, the sodium borohydride and the organomercury reagent are the dead giveaways for these. And both of these reactions are Markovnikov regiochemistry, meaning that the most substituted carbon gets the alcohol group at the end of the day. The hydrogen that is least substituted on the carbon gets the hydrogen, right? And so in OChem1, we learned 3 different reactions to generate alcohols, right? These were the first 2. And of those 3, I reiterated many times that there's only one that is anti-Markovnikov in terms of its regiochemistry, and that was the hydroboration oxidation. And so for those of you who had me for that class, you probably remember that I like to mix up, so hydroboration oxidation, I like to mix up molecules which contain multiple alkenes and then control the stereochemistry to functionalize one in Markovnikov fashion and then functionalize another in anti-Markovnikov fashion. And so the dead giveaway for whenever we were dealing with hydroboration oxidation was the use of basically boron. Now, this is not boron as in sodium borohydride, the reductant, but in the first step, boron, as in this reagent here, BH3, is borane, B-O-R-A-N-E, right? And then I mentioned to you that depending on the textbook that you're using, if you're using the one that we call for this course, which is by Klein and is generated by Wiley, which is the same company that does a lot of peer-reviewed publications, and so there's a lot of notoriety to the textbook that I selected for this course. It doesn't use borane. So borane BH3 is the simplest reagent that you can use for this reaction. But in the textbook, it uses trialkyl borons, right? So rather than BH3, you might see BR3, in which R is 3 different organic groups attached to that. And so, the truth of the matter is there's a tremendous amount of boron reagents that can cause the transformation. BH3 is the simplest one. On my examinations, I'll usually put BH3 for this transformation, but I'm just letting you know that there's also trialkyl borons that will also do it. So if you look at the textbook and you're trying to find this reaction, you're not going to see it listed as BH3. You'll likely see it as BR3 or some trialkyl substituents attached to the boron. But then the next step is pretty clear. It's hydrogen peroxide and sodium hydroxide. That's the oxidation step, hydrogen peroxide being a strong oxidant. And so what that does, and although the starting material here, regiochemistry is not really that important because in this case the starting material is equally substituted, so it really doesn't matter which carbon gets the alcohol, but you need to remember that this was the only one in which the alcohol group goes to the least substituted carbon of the double bond. That's anti-Markovnikov regioselectivity. Another reaction, and some of these are listed in that attachment, reactions from antiquity. Another one that we went over in OChem1 was dihydroxylation. Again, this is going back to that same chapter in alkenes, so we can use the same alkene starting material. And there's 2 different ways that we can run this reaction. In OChem1, we introduce a rather nasty reagent that if I have to absolutely use it, I will, but I usually will avoid it. It's known as osmium tetroxide. right? So OSO4 in the presence of hydrogen peroxide, all right? That's one way that you can run this reaction. And what it is it basically oxidizes both of the carbons involved in the double bond so that you generate a 1,2 diol, all right? Now, the stereochemistry of the 1,2 diol is really important because this follows what is known as syn hydroxylation. And syn hydroxylation means that the hydroxylation is going to be added from the same side. So there is a stereochemical outcome to this reaction in that it gives you exclusively the cis 1,2 diol product. Okay? So in this case, the stereochemical outcome might not be important, but if you were doing this reaction with something like cyclohexene, where you had a rigid ring, then the two alcohols there, the 1,2 diol that you would synthesize, would either be both popping out towards us or both popping out on the plane of the screen, so in the cis stereochemical configuration. Excuse me. Died over here, my gosh. Sorry about that, I got huge allergies. Unfortunately, it's my hometown. Oh my gosh. This one sucks. This is my hometown. So like in the spring, I have hometown allergies that I don't have anywhere else on the planet that I can speak to. All the flowers that are popping up are just dying. I'm just dying. The minute I leave Corpus Christi or Texas in general, like I've lived in Chicago, I lived in LA, I lived in China, I've been to all over the world. Only in Corpus Christi do I get allergies in the spring. All right, so a really strong oxidant that we learn is potassium permanganate, KMnO4. So we don't learn this transformation to generate the syn hydroxylation of an alkene in OChem1, but I'm introducing it to you now. You can use this oxidant in the presence of a hydroxide base in water to pull out the same transformation, which is really kind of nice because it means we can avoid osmium tetroxide. And so in OChem1, for those of you who took it, you remember I talked about why that results in the syn hydroxylation. The shape of osmium tetroxide, it's like an X. So dead center, you have osmium, and then you've got basically 4 oxygens. It's kind of like carbonyls, but they're to the metal center. And so if this represents the carbon-carbon double bond, what happens is osmium kind of comes down and it hits the double bond so that oxygen's added from the same side, right? So that collision in 3-dimensional space means that oxygen is delivered to the same side, so that's why you get syn hydroxylation. You get exclusively the cis 1,2 diol if you use that methodology. Sorry about that. And then that was really loud. So for those of you who might be recording, make sure you put your headphones off in that case. Does anybody still need this up? All right, so now I'm going to show you a really cool reaction that is very much an SN2 reaction. But what it is that we're going to generate alcohols from acetylides, which are going to react with carbonyls. And then we're going to revisit the same type of reaction with some Nobel Prize chemistry. This is really my point. So one of the things that we talk about in OChem1 in the chapter of alkynes is that there's 2 types of alkynes, right? There's an internal alkyne where if you're looking at the 2 carbons involved in the triple bond, to the right and to the left of that triple bond, you might have other alkyl groups. That would be an example of an internal alkyne. If, for example, the last 2 carbons of that chain is the triple bond, then on one hand side you might have the alkyl group, which is an R group. On the opposite side you might have what is known as the acetylenic hydrogen. Okay, so the acetylenic hydrogen, of course, would be that one. One of the things that we learned is that hydrogen is acidic. It can be pulled off if you have a strong enough base, right? Now it turns out that sodium hydroxide is not something that can pull that off. So your typical hydroxide base isn't going to do it. One of the things that we learned in OChem1 is that if you drop in elemental sodium, right, and this also works with elemental potassium, it'll do the exact same thing that we talked about earlier in discussing the acidity of alcohols, right? If we drop in sodium or potassium with alcohol, you deprotonate the alcohol to trap it as either the sodium alkoxide or the potassium alkoxide. If you do this with the terminal alkyne, what you end up generating is the deprotonated acetylide. And if you use sodium metal, then this becomes the sodium acetylide salt. If you use potassium, it's potassium acetylide salt. And so this is really fantastic because now you've got a really pissed off carbon, right? Its carbon does not have a full octet. It is now a carbon anion, and it really, really wants to get that hydrogen back, and it's willing to steal it from anywhere, or it can get, what it needs, because it's got extra electrons there, by attacking some sort of electrophile, right? So this is basically a really, really, really strong base that is absolutely nucleophilic, right? So, we see those substitution reactions with sodium hydroxide, OH minus. Well, this is like that on steroids, right? It's basically a carbanion. And so what ends up happening is that you can take your acetylide anion as its sodium salt, and if you introduce it to carbonyl containing compounds, and so in this case, we have this, I'm not gonna basically say what the R groups are, but let's just say that R2 and R3 represent different alkyl groups coming off the carbonyl. This is a ketone, and ketones have an electrophilic carbon about them because the oxygen is electron withdrawing. We can draw the polar bond there, and it's strongly electron withdrawing for a carbonyl, and what that means is there's partial positive charge on that carbon, making it electrophilic, and then setting the stage for nucleophilic attack of that carbanion to that carbonyl carbon, right? Now, if you can't just add a bond to that carbon, because if you did so as drawn, you'd have a Texas carbon, right? Which means it'd be 5 bonds to carbon. So once that attack takes place, that pi bond there breaks, donates electrons onto the oxygen. And so now whatever R1 was on the acetylide, along with the triple bond, has now made a brand new bond to the carbonyl group. And in opening up that carbonyl, you generate an alkoxide, right? Which now sets the stage for, hey, we got an OH minus. If we're trying to convert that to an alcohol, what do we need to add to it to do that? Well, it's got to be a source of hydrogen, which is basically an acid, right? So if you hit this then with hydronium, or acid and water, or an acid source, then you just protonate that O minus, and you can do this during the workup of the reaction. And you end up with your alcohol. But more importantly, in this case, you end up with not a primary alcohol, not a secondary alcohol, but that is a tertiary alcohol. Right, so we have R1, R2, R3, R2, and R3 were the two alkyl groups that were at the alpha positions relative to the carbonyl carbon. And then of course the R1 is the alkyl group that was appended to the acetylide anion. So this is really, really powerful chemistry, right? We're opening up carbonyls to be able to do this. Now, one of the problems with this is, in order to pull this off, you got to work with elemental metals, right? And that can be really problematic. Elemental metals are highly, highly reactive, right? And to help you kind of appreciate how reactive they are, I mean, just look at where they sit on the periodic table, right? Sodium and potassium are on the far left of the periodic table, which means that they're really one electron away from the nearest noble gas in the row on top of them, right? And so elemental metals like sodium and potassium will just give up electrons so that they can achieve the electronic configuration of the nearest noble gas on the upper, whatever the noble gas is, one row up on the other end, right? Which is why they readily, form ionic bonds with things like chloride and hydroxide anions, right? Those kinds of salts. And so if you were to ever purchase elemental sodium, they don't just give it to you in a box. It doesn't just come in a jar. I mean, it comes in a jar, but it's not just there by itself, okay? It's so reactive that if you take it out into the atmosphere, it will react with the water in the atmosphere and give its electrons to the water. And that interaction produces a tremendous amount of heat, and it generates hydrogen gas. The heat from the reaction is so much that it then causes the hydrogen gas to burn. So exposing elemental sodium and elemental potassium to just the atmosphere, it will explode, right? And if you look at YouTube videos, you know, it's kind of fun to play with it if you get your hands on some, because what people will do as a demonstration is they'll take a little thing of water and they'll take a tiny speck, and of course they'll put a blast shield, at least they should, and they'll drop it in there and it kind of, you know, pops around and starts popping. But there's really nice videos on YouTube where people take chunks of these things and throw them into lakes. And if you really want to piss off somebody, you throw a chunk and flush it down your roommate's toilet. You know, don't do that, please. It's just fun to think that what that might do. Hopefully the toilet's clean. But yeah, so that's a problem. So then when you buy these metals, they actually come stored in oil, right? They come stored in oil because oil is hydrophobic. And so as long as it's in oil, it's not going to react. And so you take out the elemental sodium, you gotta wash all the oil off with hexane. You gotta hope that the humidity is not like it is in South Texas, because if you're gonna try to pull off this reaction, it might explode in your hand, it might explode in the flask before you have a chance to seal it. Like, this reaction is really nice, it's really powerful, but it's problematic, right? That's basically the bottom line, right? You're gonna try to do this, like, good luck. I'm not doing this in my house or in my lab, right? Now, in comes Victor Grignard, who wins the Nobel Prize for the chemistry that I'm about to show you. And this is where we get our first glimpse of what is known as organometallic chemistry. So organometallic reagents are exactly what they sound like. And we offer a really cool class that's taught by Dr. Ben Karimi, known as inorganic chemistry, that touches base on a lot of these inorganic complexes, organometallic complexes. And what it is metals have a lot of extra electrons, and they can form what are known as dative bonds or coordination bonds with organic molecules. And oftentimes, those coordination complexes are actually really nice catalysts for a lot of different transformations. And so his class talks a lot about that. And so one of the organometallic reagents I'm going to draw, you might have seen for those of you who took me for OChem 1, because in the first exam of OChem 1, in our discussions about polar covalent bonds, we typically show that a carbon-halogen bond has the net effect of making the carbon electrophilic, because in that case, between carbon and a halogen, the halogen's the most electronegative atom, which means carbon loses electron density to that halogen. But whenever you look at a organometallic reagent such as this, you now have a carbon-magnesium halogen bond, all right? And so if we look at that carbon-magnesium bond, and magnesium is all the way on the left of the periodic table on the second column, then which atom is more electronegative? Is it magnesium or is it carbon? It's carbon. Yeah, so in this case, what you find is that if this is the most electronegative atom, the flow of electron density is actually reversed, right? And again, just to point out, typically what we see for alkyl halides is the opposite, right? So now that we have something like this in hand, and we say, all right, this is great, because it means that we can generate what is effectively an anionic carbon. And then if we go with the good old alkyl halide, this generates the electrophilic carbon. So then we can really sort of switch the roles that carbon can play for different reactions. So in OChem 1, at the end of the semester, what we learned from the reagent on the right is that we can do substitution chemistry at that carbon, all right? The situation on the right. Right? So if this is electrophilic, then we can put in a good nucleophile. The nucleophile will attack that, kick off the halogen, and then you trigger an SN2. all right? But if we were to somehow be able to put magnesium in between those two atoms, then the nucleophile is carbon. Just like what we saw in the previous example for the acetylide, which is basically like a carbanion. So the carbon is then negative, it's got extra electron density, and the carbon can then do the attacks for SN2 reactions. And that's really awesome, all right? Now, the cool thing, again, this chemistry is just really, really amazing. It was put together by Victor Grignard, and he won the Nobel Prize for the chemistry we're about to show you in 1912, all right? And this reagent here, this is known as the Grignard reagent. And this is normal chemistry that we would do in a teaching laboratory. The problem with this chemistry, and I'll tell you at the onset before we get into it, the reaction has to be bone dry. Water reacts with the Grignard reagent very fast to deactivate, which means that it's not something we can usually do here in South Texas because the humidity's so high. In order to do a reaction like this, like I could probably do it in my research lab, pretty sure we run dry reaction all the time, we would have to take all the glassware, the stir bar, everything that's going to connect to the reaction vessel, and we're going to put it in the oven at 120 degrees for about an hour or two. We're going to take it out, we're going to seal it all up, and we're going to put a vacuum on that so that it cools under a vacuum so that there's no water condensing on this thing, all right? Then we can transfer via a cannula, which is a double-sided syringe needle, the dry solvent and all the reagents into the reaction vessel, right? And at this point, magnesium's already there and it's dry. And then we can run this reaction, okay? Now, it used to be that when I was an undergraduate here, way back when, this must have been sometime in like 2003 or 2004, these reactions were run in the teaching labs, which nobody ever got in front of because the people who set up these reactions most likely either did their PhD up north, where it's, or maybe in Nevada or Arizona, where there's no humidity and it worked. Down here it doesn't. And we don't have teaching facilities to allow you to run reactions under inert atmosphere because nobody does. I mean, it's just, you guys' education is important, but like, come on, really, we're not gonna do all that stuff. You only have like really just under 3 hours to do it. So we're really playing with fire trying to do that, right? So it's a damn shame, all right? And the reason it's a damn shame is because it's such an easy reaction to run. All you do is you take your alkyl halide and you take elemental magnesium. And elemental magnesium is not like sodium and it's not like potassium. You can hold this stuff in your hand and it's not gonna pop. Magnesium does oxidize, kind of like silver, right? Like silver as a precious metal will oxidize. Copper as a not so precious metal will oxidize. You'll get oxides on the surface. So you take elemental magnesium, you get like a wire brush and you just kind of scrape off that oxide layer. Just put it in your flask, you put your alkyl halide in there, and usually the solvent is ether, which doesn't like water. And all you do is stir these things around, and lo and behold, magnesium just inserts itself right between them, and that's it. And the cool thing about it is, in order to do the next step of the reaction, you don't even have to shut that reaction off. You can then just inject whatever it is you want to do for the substitution in that same reaction flask. So you can run the second reaction as what we call it in situ. You generate this Grignard reagent in situ. You can isolate the Grignard reagent if you wanted to. You don't absolutely have to, okay? But it's so easy. It's so easy to make. And this reaction for the conversion to form the Grignard reagent works best for alkyl iodides, followed by alkyl bromides, followed by alkyl chlorides, and it doesn't really work very well at all for alkyl fluorides. Right? And so this is fantastic. It means you can do this chemistry very easily. And so let's say you have something like bromobenzene. And so you can already start to see how, I might put something on the exam. Hey, here's benzene. I'm going to throw bromine at you and iron tribromide. What are you going to get? Oh, you're going to get what I just drew here, right? It's an electrophilic aromatic substitution. Put a bromine in there. Next step, Dr. Olson says, throw some magnesium on it. What's going to happen? And all it is just, here's that aromatic system, magnesium there, and then you get the Grignard reagent, right? Don't want to do it with an aromatic group? No problem. It even works with alkyl halides. It works with cycloalkanes like monobrominated cyclohexane. And you can basically get that magnesium to insert itself there. Now, this is game-changing chemistry. For one, it's not that dangerous, right? Unless you light the fire with ether, which usually happens to be the cause for most fires from people making crystal meth. In case you're wondering why those labs are always going up in flames, it's because they use ether in the synthesis at a high vapor pressure. If you're not careful, ether is one of those gases. It's highly flammable. It off gases from the liquid. It's more denser than air, so it accumulates on the bottom. And usually, if you have a stove that's on a gas flame, that causes some sort of explosion. Right? So we can make this stuff really easy. Now, the cool thing about this reagent is what Victor goes on to show what you can do with it. And he goes on to show, and we're going to see this for several chapters, that you can make all kinds of alcohols with it if you design them right. The other cool thing about Victor Grignard, and this is kind of a story that touches on my chemistry when I was in grad school, right? I worked in Dr. Fraser Stoddard's, Sir Fraser Stoddard's lab both at UCLA and at Northwestern, starting from 2005 to 2010, right? He won the Nobel Prize for his body of work from the time that he was a PI till 2016, of which the work that I contributed to was part of that large body of work. And he publishes this book known as The Nature of the Mechanical Bond. A lot of my 21 papers out of his group are in that textbook. And there's figures that I made in that textbook, which is cool, all right? But he wins the Nobel Prize. I don't get anything, right? He gets invited to go see the king and queen, and he gets the gold medal, and I got a nice picture where I'm holding it. It's great. And then I get the recognition of like, oh, you trained under him. And the people who train under you are really good. And then his academic pedigree goes all the way back to Bunsen, a bunch of very famous people. And it's cool to be a part of that family. But he gets the $1 million, or he spits the $1 million. I don't see any of that money, okay? That's not what happened with Victor Grignard. The chemistry I'm about to show you was so pervasive and so much of his work, and this was the graduate student in another PhD's laboratory, and he won the Nobel Prize, not his PI, right? And when they went back and looked at all the body of work, there was very, very little intellectual property of that PI in that work, that this is an example of where the graduate student won the Nobel Prize, all right? So it's a really cool story. So now I'm not telling you this to go join a research lab and be like, yeah, I'm gonna get all the, you're not gonna win the Nobel Prize, it's gonna be your PI. Unless you do something like this, all right? So before I get into that chemistry, let me show you an alternative. I showed you the acetylide alternative. Here's another alternative, right? You can do basically the same type of chemistry using the acetylide I just showed in the previous notes, or using another stupid reactive metal known as lithium, right? So this chemistry is also, really nice. You can generate what are known as organolithiums. To do the exact same chemical transformations that I'm about to show you, right? But he wins the Nobel Prize because one, you don't have to work with the deprotonated acetylides. Two, you don't have to work with lithium metal, which is just like sodium potassium. That's something you really want to be messing around with, right? Because if you take those things, sodium, potassium, lithium, and you drop an organic solvent, it's going to explode, right? Water already catches fire, but water's not that flammable. But if you put it in methanol or something like that, it will explode. So yeah, you win the Nobel Prize when you solve a problem like that, right? Doing the same chemistry that's not as dangerous, and then you go on to show that these reagents readily attack carbonyls. Now, whenever you see organolithiums or Grignard reagents, whatever that R group is that's bonded to the magnesium or bonded to the lithium, you should treat that carbon as if it's R minus. Just treat it like it's R minus, right? So no matter whether or not you're looking at the Grignard reagent or you're looking at the organolithium, whatever that R group is, it is a carbanion, and thus it is nucleophilic, and thus you can use it to trigger substitution reactions, right? And he goes on to show, in one of many different instances, that if you have a carbonyl, just like we drew for the acetylide chemistry, that there's nucleophilic attack of that carbon that makes the bond to the carbonyl, pops open the carbonyl to generate an alkoxide. And now you have your deprotonated alkoxide. And then at that point, all you got to do is expose it to an acid aqueous workup of some sort. And you get your tertiary alcohol. Very nice, very quick, but more importantly, safely. Right? Safely, that's a big thing. And so not only does he go on to show that you can generate this, right? Because I showed you in the previous page that you can use the acetylide anion to generate the tertiary alcohol, in this case if you reacted with a ketone. He also goes on to show that if you did this reaction with formaldehyde, we're going to do this in the next page, you can generate primary alcohols. Then he doesn't stop there. He goes on to show that if you do this with regular aldehydes, you can generate secondary alcohols. So now on the menu is primary, secondary, and tertiary alcohols. And if you design the materials right, or you choose the starting materials and whatever the carbonyl compounds are, judiciously, then you realize, like, oh man, you can make whatever alcohol you want using this chemistry, whereas every other means to which to do this was actually would be dangerous. That wins you the Nobel Prize. That gives you the Nobel Prize and not your PI. And his body of work is just enormous, right? Absolutely enormous. So this wasn't like a team effort, like the body of work for Fraser Stoddart, where I'm just a cog, and then so were all my colleagues. And we get, people know who we are, what we did, that's it, but we don't get the prize. But this guy was all his work, right? Awesome. Anybody still need something? All right, so let's take a look at some of these approaches, right? So I've sort of said them, and now we can get an idea. So what we're looking at is addition to formaldehyde. And when you use formaldehyde, that gives you the primary alcohol. Now you probably have heard of formaldehyde. Formaldehyde for storing specimens for those of you biology majors, right? If you don't know what formaldehyde is, that's formaldehyde, right? It's a gaseous aldehyde. It's not like a traditional aldehyde, which is usually the carbonyl at the end of an alkyl chain. There's a single carbon in formaldehyde, which means alpha to the carbonyl, there's two hydrogens, right? But what it also means is depending what your R group is in the Grignard reagent, you can generate the primary alcohol, but you extend that chain by a single carbon link, right? Which effectively means that if you wanted to make my favorite compound, which would be ethanol, which has two carbons, then your Grignard reagent better be a single carbon argon, which means you would use maybe, chloromethane to generate the Grignard reagent, then you add that, and now that puts the second carbon, and you can produce ethanol. Or if you wanted to produce propanol, it means your R group would have two carbons in the chain. The formaldehyde would contribute the third, and you'd get your primary alcohol like that, right? If you wanted to, again, go back to an aromatic system, so you have your aromatic halide introduce the magnesium. If you hit this with formaldehyde, then you can generate benzyl alcohol. So already really simple. Addition to aldehyde. And this would be a more traditional aldehyde. gives secondary alcohols. Right? And so all it is a matter of, are you counting your carbons, right? So every time that I teach this class, I always get somebody in the class who, gets this wrong and then asks me, how do I figure out how to do these right? Because I keep screwing it up. Just count your carbons. That's all it is. Just count your carbons, right? So if you look at formaldehyde has one carbon. If you look at a normal aldehyde, usually you have the carbon of the carbonyl, you have this other carbon, and now we're adding a third carbon to the carbonyl carbon. So if you do 1, 2, right, then you already know you're going to be generating. So here's briefly draw the mechanism. I'm going to assume that we have H plus workup. We have R, carbonyl carbon, alcohol, R sub 1, and then hydrogen. So in this case, this is a secondary alcohol. Right? So he finds a really cool way to generate primary alcohols, tertiary alcohols, and secondary alcohols simply by choosing to react with formaldehyde, regular aldehydes, or ketones, right? But remember, the reagent here is that the carbon is anionic. It's a nucleophile. So it doesn't just stop there. No. This guy does a lot. And he goes on to show that they can even react with epoxides. For those of you who took chemistry with me, or Chem 1, you will remember the epoxides as party hat. I put a party hat synthesis on the exam. That's a reaction from OChem 1, right? It is the peroxy acid reacts with carbon-carbon double bonds to generate the party hat. There it is. And if you think about what's going on here, this is a polar covalent bond, which means the two carbons, right, and the epoxide ring are electrophilic, which means they can be exposed to and undergo nucleophilic attack. And so the attack from the R minus will attack one of those carbons. That triggers a ring opening of that epoxide. And so once that has a ring opening, lo and behold, hey, it's an alkoxide. And then you trap it, it gets trapped momentarily as a magnesium salt, as it is the case with all these reactions, right? And then all you have to do, like in every single other reaction, is hit this with hydronium, which is just a little bit of acid and water to protonate that O minus. And now you get a primary alcohol that you've extended now by 2 carbons, depending on what your R group was from the Grignard reagent. So, very cool chemistry. Very, very cool chemistry. I think it's this chapter that we even discuss epoxides in general. We'll see when we get there. We're going to see a lot more of this stuff. And so in practice, if you had an aromatic Grignard reagent, and let's say we did, hey, step 1, we expose it to 1,2-epoxide. Step 2, we hit it with acid and water and the workup hydronium. And all we're doing is increasing the R group by 2 carbons. These 2 carbons right here that I've circled are the same 2 carbons that are in the epoxide. Right. It's beautiful chemistry. Amazingly simple. Now, I do want to point out that there are side reactions that we have to be mindful of, and I've already kind of alluded to what it is, right? Because the idea here is that if this reagent behaves as if you have a carbon anion, then as I pointed out before, this is something that is very basic. And we know it's very basic, right? Because the pKa of a hydrogen on methane is greater than 60, right? And the joke that I give in OChem 1 is like, I'm glad that it is, because if you're in a hot tub with a bunch of people, you can fart all you want, and it's only gonna smell bad, but the pH of that solution is never gonna drop, right? So thankfully, that's not something acidic, but this is very, very basic, because if the pKa of methane is greater than 60, imagine how hard it is to steal that hydrogen, right? It's very, very hard. So when you do it with something like this, and it behaves like that, then it really wants to get the nucleus back. So it's extremely basic. And as a result, as I pointed out to you, it will readily react with water to deactivate. Okay? So if you have your Grignard reagent already made, and if you spit this reaction, you're done. And not only are you done, but you've screwed up badly, because it deactivates as an alkane. And then you get magnesium hydroxide. And so it's not only just that the solution has a high pH, but what was the starting material for the Grignard reagent? It was an alkyl halide. And if you looked at the reactivity of the alkyl halide, right, if you use the iodide, it's better than the bromide, it's better than the chloride. And guess what? When you go to Sigma Aldrich and you want to buy those alkyl halides, the one that reacts the best is the most expensive one. Alkyl iodides are more expensive. Alkyl bromides are less expensive. Alkyl chlorides are less expensive. Alkyl fluorides are cheap. They don't do crap except poison our water and things like that. So you start out with an expensive alkyl halide. You add in really cheap magnesium to do what is going to be a safe reaction, but you ruin it. You either spit in it, you pee in it, you open up to atmosphere and it's wet because you're in South Texas, and you, let's say it was, I don't know, ethyl or bromobenzene. You just get benzene back. Bromobenzene's way more expensive than benzene. So if you do this in industry, you're probably going to get fired, because the likelihood is high that you did this on a multi-kilogram scale, right? So you take a step back in complexity, you lose your money in the process if you don't watch out. Now, you could use this mechanism to your advantage, because instead of exposing it to H2O by accident, you might be interested in exposing it to D2O on purpose. And if you don't know what D2O is, that is heavy water. D is not an element on the periodic table, it is deuterium, which is an isotope of water, and it is radioactive. Not radioactive, but it can be addressed in instrumentation like nuclear magnetic resonance spectroscopy. So early at the beginning of the semester, when we were talking about NMR spectroscopy, and we were looking at the hydrogen signature of a bunch of organic molecules, and I said, hey, what happens if you take this molecule and you dump it into a swimming pool of acetone? Acetone has 6 hydrogens on it, right? So that acetone would give us a huge signal if we didn't deuterate those hydrogens, and we do. So rather than acetone where it's H6 on the molecular structure, it's actually D6. Those hydrogens are deuteriums, and that makes that acetone really, really expensive, because then it's NMR silent. And so then the question is, well, how do you start to put deuterium atoms on different parts of organic molecules? Well, it's that in their synthesis, if instead of using, for example, H2O, you can use D2O, as we are in this case, then you can deactivate that alkyl halide, whatever it was, and convert it to a radio-labeled deuterium isotope, right? And that is really cool, and you can design a lot of cool stuff like that. And maybe you can do this on purpose if you wanted to, rather than, just saying, hey, it's always water. It doesn't always have to be water. You need to. It's a lot to consume, I know. and try to make it entertaining, and lo and behold, I just threw like 7 reactions at you. And it's only 117. There are so many ways to make alcohol. So many ways. It's almost amazing. I was just thinking about how we're running out of water in Corpus Christi. I went to the kitchen and I have this cabinet in the corner. It's full of alcohol. I still have water. It's just a little bit of alcohol. So, one of the things that I hope you wrap your mind around, we learned in OChem 1 about reduction oxidation chemistry. And in the context of organic chemistry, anytime we do an oxidation, we're adding oxygen back into it. So we're removing from the definition of electron donating, electron accepting. I mean, that's the standardized definition for these things. It still applies, it's better for us to think about what happens when we say, hey, it's oxidized, or hey, it's reduced. Usually if it's reduced, we're adding hydrogen back in, and we're removing either halogens or oxygens. So it means that if we have something like a carbonyl is 1 step higher in oxidation from alcohols, right? So in the chemistry where we do the synthesis, we have the alkene, we oxidize it to the alcohol. You can oxidize that further, depending on whether it's a secondary alcohol or a primary alcohol. You can generate ketones or aldehydes, which means you should be able to go backwards, which is what we're going to talk about now. How do we go backwards from carbonyl-containing molecules 1 step in oxidation state to the alcohol? And in order to do that, we're going to deliver what is known as hydride ions. Okay? Hydride ions are H-. And if you introduce hydride ions into carbonyls, that's how you can convert them into alcohols. And there are 2 principal reagents. One of them you've seen before, one of them you have not. The first one is LiAlH4. That is lithium aluminum hydride. It is commonly abbreviated as LAH. I would spend some time memorizing both of those, because usually when I write your exams, I can't make up my mind whether I want to write it as LAH or LiAlH4. And I usually don't like to stick with one or the other, because you might see them both. So it's good to learn both. The other one you have seen before, especially today, one of the reactions that we went over was a reductant that's pretty common. That's known as sodium borohydride. Okay, so the structures for these look like this. They are salts. Here's the lithium aluminum hydride salt. Here is the sodium borohydride salt. So we're talking about these 2. Here's the substrate. In this case, the substrate is cyclohexanone. So it's cyclohexane with a ketone on it. And the attack, just like we saw before, goes to the electrophilic carbon, which is the carbon of the carbonyl. To avoid a Texas carbon, that carbonyl pops open. One of these hydrogens on the borohydride then gets added, so BH4 ends up becoming borane, which is BH3. I think there's somebody out there with a skateboard. Hey, Tony Hawk. That's an old joke. You might not know who Tony Hawk is. If you do, it's probably because you play this game. You're too young to actually watch it. Anyway. So yeah, look what happens. It's almost the exact same thing that we saw for the acetylide. It's almost the exact same thing we saw for the alkyl lithium. It's almost the exact same thing we saw for the ingredient. you have a nucleophile attacking the carbonyl, you open it up, you generate an alkoxide, which basically means at this stage, all you have to do is hit it with some acid, so hydronium it is, water and acid. And in this case, you get secondary alcohol. So NaBH4, that's right, that it is used to reduce ketones. And aldehydes, but not esters or acid chlorides. Right? So what is this basically telling us? It's basically saying that if you want to work this chemistry on carbonyl-containing molecules that are ketones or aldehydes that use sodium borohydride, but Dr. Olson, carboxylic acids and carboxylic acid derivatives such as acid halides and esters and amides and things like that. What about them? Well, sodium borohydride doesn't work. It's not strong enough, right? If you want to do that, you have to use lithium aluminum hydride, which is the other one. Lithium aluminum hydride is a much more stronger reducing agent than sodium borohydride, which is why we haven't seen it in OChem 1 for those reactions in the chapter about alkenes and alkynes, or why we introduce it in OChem 2. Alright, so here is an aldehyde. All we're going to do is NaBH4. And there it is. In this case, primary alcohol. And so just like we saw before with Grignard's chemistry, if you do this chemistry on a ketone, you get a secondary alcohol. If you do this chemistry on an aldehyde, you get a primary alcohol. Right? Because it all comes back to counting carbons. If it's a ketone, then alpha to the left and alpha to the right of the carbonyl are two other carbons. So if you reduce that carbonyl to an alcohol, then there's two carbons connected to that carbon. It's a secondary alcohol. For this, alpha to the aldehyde is a hydrogen and a carbon, which means that it's a primary alcohol. Now, for those of you who don't remember what esters look like, right, here's an ester. It's a carboxylic acid derivative. It's formed from the reaction of alcohols and carboxylic acids. And so for this, if we hit it with lithium aluminum hydride, what you're going to see is chain cleavage from the carbonyl-carbon alpha to the oxygen. So you basically break the ester bond. That's how you should think of it. These two carbons, which I'm about to circle right here, okay, so I'm circling those two carbons, which are alpha to the left, going upstairs to the left. Those are these same carbons right there in the mid primary alcohol. So I will write that LAH will work on everything. It's much more reactive. What I will also say is LAH will not work on water. For all things. And the reason for that is just too basic. All right, I'm gonna try to squeeze in one more reaction in here. This is definitely switching gears from the conversation we're having, although giving us the same type of chemistry. The reagent here is known as Raney nickel. Now, I want to point out to you that if it's not Raney nickel and it's just nickel, regular good old nickel, it's going to do something completely different. It's going to do exactly what palladium charcoal does. It's going to do exactly what platinum oxide does. And for a molecule like that, it just gets rid of the carbonyl completely. But if you use Raney nickel, it's a reduction reaction, but it's not complete, and it will stop at the alcohol. So you throw palladium on charcoal at this, and the carbon is gone. That's it, it's just gone. You get alkane. Right? Just like alkenes become alkanes, alkynes become alkanes. Same chemistry, except Raney nickel, you get to the alcohol. Anybody still need this up? I like when I ask that question and nobody answers like it's just right. All right, time for some stinky chemistry. Stinky, yes, that's it. In the chapter of alcohols is a section that doesn't need its own chapter because the reactivity is very similar, and it is the thiols. The only difference between alcohols and thiols is instead of oxygen, it's sulfur. And that stuff stinks. Right? So going back to my thing about farting in the tub with a bunch of people, the pH is never going to become acidic, it's just going to smell bad, and it's not because of methane. Methane doesn't smell. It's odorless. Right? Natural gas is odorless. We have to spike it with stuff that stinks so that if you have a gas leak in your house, at least you know not to like either shut it off or that it's going to explode. It's the same thing with your butt. What you're smelling is not the methane, it's the byproducts of the bacteria in your gut, and the molecules that they produce are thiols. And it's really strange because we have such a sensitivity to detecting thiols. It's amazing. You can smell fart from across the room. You can smell the thiol in the natural gas from the oven if it's leaking very easily. We use that to our advantage because we know, and I don't know why, maybe some of your biologists can tell me what, maybe it has to do with the fact that volcanic and type stuff like that involves sulfur and you need to be aware of that or acutely aware of that. I don't know. All I know is that if somebody farted up there, I could smell it. And in chemistry and in physics, we would say that the detection kinetics is diffusion limited. So the closer you are, you can smell it before I do, because I'm far away, it takes a while to get here. All right? So we'll talk a little bit about some of those molecules, but they're basically analogs of alcohols, which makes this topic even more interesting to me. The only difference, as I pointed out, instead of an OH, it's an SH group. Now, these SH groups are known as mercaptans. I'll tell you a couple of funny stories. Mercaptans is mercury capture. Because it turns out that sulfur binds very strongly with even metals, particularly mercury. Particularly mercury. When I was a graduate student and I was running synthesis. I was using a mercury thermometer, and I made the mistake of using the wrong oil in my oil bath that I was heating up. It turns out at the time the hot plates that we used were pieces of crap, and if the circuit fails, it fails with a closed circuit, which means, if you know how a hot plate works, it's basically a resistive element that you control the voltage coming from the 120 line. And as you run current through something that's a resistor, right, it doesn't allow the current to flow very easily, and what it does is that resistor starts to get hot, and then you can control the temperature of the resistor by controlling voltage. When the hot plate fails, for this particular brand, it was a closed circuit, which has got the full 120, that hot plate started glowing, it caught the oil bath on fire, and the whole thing just caught on fire. And I was in LA, relaxing, and I got a phone call from the postdoc in the lab. It was like, hey man, your fluid had a fire, you need to come clean it up. So I get there, and the first thing he says is like, hey, you're using a thermometer in that? I was like, yeah. He was like, what kind of thermometer do you use? I'm pretty sure it was a mercury thermometer. He's like, crap, I'm hoping you wouldn't say that. Because nowadays, there's 3 types of thermometers, right? There's the old school mercury thermometers, which work really well. Now you can get the alcohol versions of those, which are much safer. And then you can get digital thermometers. My lab uses digital thermometers, really we use oil baths. We use sand baths and hot plates that have like this shape of the flask. So basically what's happened is the mercury thermometer melted, and the whole fume hood, the inside became a vapor deposition experiment. That there was atomic mercury all over the place. And I had to clean that up, which meant I had to get suited in like a hazmat suit with a respirator and all that good stuff. And I had to go in there and clean it. And then they give you this chemical that you don't know what it is. And so because I didn't know what it was, like any good chemist, I went and looked up to see what the structure was. And it was a surfactant, which is a detergent kind of soap, right? But it wasn't just any soap, it was a soap that contained sulfur atoms, thiols. And this soap is specifically designed so that when you scrub things, it bonds to the mercury metals until you actually remove the mercury from wherever it might be. Right? So elemental mercury is pretty toxic. You can actually eat it, and nothing's going to happen to you. It's toxic when it's in the gas, and you inhale it. Then that becomes a problem. Right? And so now that there's this atomic mercury everywhere, that's why I have to be in the hazmat suit. So I ended up learning about why mercaptans are mercaptans. Because I made the mistake of using the wrong oil in my bath. I later found out that I used mineral oil when I should have been using silicon oil, which has a higher flash point, right? And that would have maybe saved me the trouble. But now I'm here telling you this story, and now hopefully you don't forget it. Not to make the same mistake, but also that thiols can bind mercury. And they also bind other metals, and I've got funnier stories I'll tell you later when the time comes. All right. And so, just like alcohols, they're named like alkane thiols, which basically means if you know what the alkyl group is and how to name it, then you just say, oh, there it is, something thiol. So, something like this, which would be analogous to my favorite compound in the world, except it's a thiol, there's 2 carbons, what's the prefix for 2? It's ethane thiol. And it's that easy. So if I give you something like this, with 1, 2, 3, 4 carbons, that's butane. Butane thiol is all it takes. Right? Now, if you're lucky, I'll give you a problem like that. If you're not so lucky, usually is the case, I'll give you something that looks like this. And hope you remember the lesson that you learned here. That thiols take priority over alkenes, so the numbering system would be right to left. Meaning we have a double bond in carbon 2, the thiols in carbon 1. So it's very similar to how we name the analogous alcohols, except it's a thiol. So 2-butene. And I want to point out to you, like I did before, that is not an A, that is an E for the E, but it's not E, it's N, 2-butene, 1-thiol. Now, one problem is on this chapter earlier, when I gave you the priorities, I don't think I listed thiols there. So I'm going to write this just once. These do not take priority over alcohols. Alcohols have priority over thiols. Okay? That's a really important thing to remember, because now it sets the stage for me to show you, all right, if the base name is a thiol, then what do we call it if it's a substituent? So here we have a 3-carbon containing compound. If the alcohol takes priority, that means this gets carbon 1 because it's the priority over the thiol, which means numbering is like this, okay? The thiol group as a functional group is mercapto. So this would be 3 mercapto prop, so then it becomes propanol. Now, one of the molecules that we spike into our natural gas is very similar to this. It's actually mercaptoethanol. And when I was an undergraduate student in a class about this size, we had a bottle of mercaptoethanol. And if you know what natural gas smells like, it smells like, you know, like spoiled eggs, it smells like ass, it smells like fart, like it's all of those things. And one of the things that my colleague, who's not my colleague now, he's my professor at the time, Dr. Eugene Billock liked to do, and we're at the CS, he would come into the class and he would kind of snicker, he would take that bottle of mercaptoethanol and he would open it up for like a second and then close it and then leave. And then people were just like, what the hell just happened? And then like after a while, the whole room would smell as if the person next to you just cut it. Bad. And it wasn't bad enough so that, you know, it overcame OSHA's like exposure limit. It's not what it was. It was that you're so used to detecting, the body's so adept at detecting that sulfur smell that even the ppms are well below the limit threshold. You could smell it like the dude next to you farted. And it was the funniest thing that has ever happened. When I realized it had happened, it was too late, and I was like, all right? That's mercaptoethanol. That's the stuff that we spike our natural gas with. So that molecule that he exposed us to for his little joke was this one, right? So it's just like 3-mercaptopropanol, except it's not, right? We can then number it 1, 2. This becomes 2-mercaptoethanol. Oh, these stories get better. Wait till we get to the chapter on carboxylic acids and I tell you how we figured out that the stuff that ants, fire ants injected to you was a carboxylic acid. It's a horrible story. Does anybody still need this up? All right. So I really think thiols are funny, because you haven't noticed. So offensive smells is what they're known for. I mean, when you think about it at the end of the day, I mean, it's not really that bad. When we get to the chapter on carboxylic acid, there's some really bad ones, like caproic acid. That is disgusting. We'll talk about that when we get to it. Go ahead and draw these compounds. These compounds are particularly bad. So in case you haven't noticed, there is a feral cat population on campus. The origins of this feral cat population is students like you guys who are like, I want to get a cat, and then you get a cat, and then you graduate, and you're like, I don't know what to do with this cat, and you just let it go. That's what's been happening for years. So there's a huge feral cat population. People feed them kind of like right between the CS and the library. They get under the gun. I mean, it's cute. I absolutely love cats. I'm a cat person. But you got to be careful when you walk around, for example, the parking structure at night, because what you see that you think, hey, that's a strange looking cat. It might be a skunk, right? Which, if you've seen any of the Looney Tunes cartoons with Pepe Le Pew, like that's the whole shtick. Is that if you remove that stripe, it looks like a cat. But it's not a cat. And I didn't know this until I moved to Chicago. Chicago is an interesting place because Chicago is one of these cities where it's a major metropolitan area, but in the city are neighborhoods. There's neighborhood bars which was just wild to me because the zoning situation in Texas is not like that, right? I could walk down the street, there's a bar in the neighborhood. I'm like, whoa, this is cool. But in those neighborhoods there, it's full of skunks, just like the parking structure area, there's a lot of skunks. I learned, and it missed me, I was on a date and we're going back to the condo I lived in and I saw a skunk and that thing was so pissed off that I was there that it immediately went like that and started chasing us and it sprayed and then I looked it up. They can hit you from like 7 to 8 feet away, okay? So don't try to feed the skunks thinking they're cats. They will spray you from like 7 feet away, right? And what they spray you with are these compounds right here, right? These are the components of skunk scent. Now, there's a huge problem with getting sprayed with this because it's notoriously difficult to get off of you, especially if it gets in your hair. Because one of the amino acids that we have that, for example, is in your hair is the amino acid cysteine, which is a thiol-containing amino acid, and cysteine bonds, and I'll allude to those later with another story, is how you lock your hair, you know, when you're born as either, hey, you have curly hair, or hey, you have straight hair. And one of the ways that you can break a sulfur-sulfur cysteine bond is by exposing it to, guess what? Free thiols. Which means that if you get sprayed in your hair, you're gonna have a very hard time getting that scent off, and then you have to go to Google and look up all those old wives' tales, like how do I get this smell off of me? It is really bad, and there's all kinds of stuff. And usually it involves using tomato sauce or tomatoes because those are acidic and you can break those bonds with an acid, right? So 1 minute left. I'll let you guys go. Have a great weekend.